There you go.
Cool.
As it happens, the other day that you guys were like all walking towards the camera, that happened to be after like the hour, so I ended up not posting it because it was like my camera after an hour it starts a new one. So like the after an hour was just you guys walking towards the camera and nothing interesting. So I thought I would, save you from your YouTube fame. And I know once you crack open that door, it's hard to close it. Internet celebrity and all, it's a hard life. Oh yeah, me. Yeah, thousands of subscribers. Which I love, but of course I fail to do the usual things that should be done to increase your number of subscribers, right? Like I should start selling merch and the rest of it, right? It's like my love language is topology. My love language is linear algebra. I think I could go that route, right? It'd sell. Actually, Dr. Smith was showing me a bunch of cartoons. I brought up as soon as I said it. He's like whipped out his phone. And he's got like 10 different cartoons for each different love language. Like he's got love language of a statistician, love language of this and that. Yeah, it's like, did you draw these? He's like, no. I was like, ah. He should put them on my website. Yeah, that'd be fun. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for students. Just ask you to help us to use this time wisely, Lord. In your name I pray. Amen. So I assume you guys have questions. Or don't have questions. I have something to do. Yes, Bethany.
For number 17, part A, if you're doing a subgroup test, I am wondering what like the inverse of sigma and isometry is. Like, what does that look like to be an inverse in that?
So the sub, I need context. Oh, thank you. 17a. You're supposed to show that the question is why is isom Rn. You want to show that that's a subgroup of the permutations on Rn by subgroup test, I said. And so you're asking me, what are you asking me?
What it looks like, what does the inverse look like for that?
What does the inverse look like? Let's see. So if sigma, as you said, is an element of the isometries of Rn, what's that tell us? Then all we know, until we prove all the other stuff that we did, but the basic thing we know is that the distance between P and Q for the images is the same as the distance between P and Q. So phi of P is the image of P under phi. Phi of Q is the image of Q under phi. I keep saying phi, but I mean sigma. So the distance between the images is the same as the distance between the inputs, right? I mean, that's the definition of isometry. So you're asking me what? What are you asking me?
What does it mean for it to be inverse? So like to show that,
Oh, inverse. So,
to show that like if you have sigma and something else in the isometry, you can show that their product or like composition is also in it, and that's not that hard. But
well.
then for the inverses, I just don't know what the inverse function is, I guess.
Yeah, one of the things I failed to emphasize in class is for a finite group, showing closure suffices, right? Actually, inverses follow automatically. There's an argument that can be given. I haven't done that in class, but actually in the case of a finite group, if you can prove that a subset is closed under multiplication, that actually is another test. You don't actually have to check inverses, but I got bad news. This is far from finite. So what you've shown already will not be enough. Like showing closure, great, good start. And I'm guessing, I think I know how you did that, but I mean, you want to show that this condition holds for sigma inverse, right? So what do you guys think? How are you going to do it? Any ideas? I mean, the only thing I can think to work with here, at this level of abstraction, at this point, is that we know that sigma composed with sigma inverse is the identity, right, on Rn, of course. And we also know that sigma inverse composed with sigma is equal to the identity. We know that sigma inverse exists, right? But what we don't know is if sigma inverse is in fact in the isometry, right? It exists as a function from Rn to Rn. That's right, because the inverse of a bijection is a bijection. So that's just math 200. I mean, the proof that the permutation group is a group is essentially math 200. It's the inverse of a bijection is a bijection. The composition of bijections is a bijection, right? Function composition is associative, these things. But we have those to work with. Does that help? Can I play some game with the condition that what we're given? I'm afraid if I write down anything, I'm going to give you the solution. I don't know. You're like, don't be afraid, just write something down. See what happens.
Can you leave it in the notation with like the d of sigma of x comma sigma of y? Because that's how I did it for the first part. But like, are you allowed to just leave it?
Oh yeah. I mean, the distance function from P to Q is this. Oh, sorry. Well, I don't know. I mean, it's symmetric, so whatever. But and so that's equal to. That's just that's you know. That's like me saying you're Bethany versus Bethany. Which do you prefer? Okay, yeah. The correct answer to that is yes. All right. So no, I think that's just notation. That's fine. Although I think that notation's easier to think in. Good choice. Let me ask you a question. So if we think about well, here, how about this? After I ask this question, I've solved this question for you. What happens if we put P equal to sigma inverse of P? And, oh, I can't do that. That's the right way to say it.
Well, I guess, what could you say, since the distance between x and y is the same as the distance between like sigma of x and sigma of y, and then but replace the distance of x and y with like sigma inverse of sigma?
Yeah, I think that's what we want to do. So you're saying the distance between x and y is equal to the distance between sigma of x and sigma of y?
Right, and then replace x and y with like sigma inverse of sigma of
Sigma inverse of x, sigma inverse of y is equal to the distance between sigma of sigma inverse of x, sigma of sigma inverse of y. So in other words, put P equal to sigma inverse of x and Q equal to sigma inverse of y, and use the blue. Use what's given in blue. I mean, that's the condition for an isometry. If we evaluate that condition at P equals to phi inverse of x and sigma inverse of x and Q equal to sigma inverse of y, then it looks like it gives us that the distance between sigma inverse of x and sigma inverse of y is equal to the distance between x and y, right? But here, x and y are arbitrary. Well, that's the thing you got to sort through. How do you say x? I mean, you need to say, you probably should say let x and y be in Rn, right? And then consider that the distance between sigma inverse of x and sigma inverse of y is equal to, I don't know, you got to find your own words here, but that's the right calculation, yeah. This is not a solution on the board, right? This is thoughts, yeah.
So you know that sigma inverse is in there just because it's a bijection.
Right. Sigma, there's no, we're not responsible for proving sigma inverse's existence. We're responsible for proving sigma inverse's residence in the isometry group, I guess. Other questions? Mm-hmm.
Part two to the question I asked in the lecture. Where did we prove, because I was trying to look through the notes and I couldn't find it. Where did we prove or at least state that the order of an element is equal to the order of its inverse?
Well, let's work it out. So the order of, suppose the order of G is equal to n, then that means that G to the J is equal to E, is not equal to E for J equals to 1 to n minus 1, but G to the n is equal to E, right? Definition of order. So consider G inverse to the n, right? G inverse to the n is G, how to say this? Yeah, G to the minus n by laws of exponents, which of course is G to the n inverse, again by laws of exponents, which is E inverse, which is E. So therefore, the order of G inverse is at most n, and then we need to prove that it can't be less than that, right? So consider G inverse to the J. I mean, I could have just done this argument in one line rather than two. Oh well, too late. G to the minus J is G to the J inverse, yeah. And so suppose towards a contradiction, well, I mean, just if that's equal to E, right? If this is equal to E, then that implies that, I guess I don't need contradiction here necessarily, that G to the J is equal to E inverse, which is equal to E. So what does that say about J? Thus J is what? J is greater than or equal to n, I suppose. I don't know. I'm sorry. This is the time of day I start to hit a... All right. Fine. Contradiction is clearer to me at the moment. Let J be less than n, yeah? Consider this. Bop, 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 bop. We have G to the J. We have G to the J equals to E, which is, of course, that contradicts that the order of G is n, right? We cannot have that G to a power less than n is the identity again. And that's what we got from assuming that there was a smaller power than n of the inverse raised to that power, giving the identity. So that's a contradiction, therefore no such... the inverse raised to any power less than n is not equal to the identity, and it follows that the order of the inverse is equal to...
Okay, so...
There's a separate argument that needs to be given for the infinite order case. Should we go through that? All right, here goes. If the order of G is equal to infinity, then what's that mean? Then G to the J is not equal to E for all J in the natural numbers. In other words, for any non-zero power, I mean, the zero power is 1 by definition. But for any positive power, it's not the identity, right? That's what it means to have infinite order. Consider the inverse. G inverse. If there exists J, in the natural numbers, such that G inverse to the J equals to the identity, then what? That implies that g to the minus j is equal to the identity, which implies that g, did I just do it again? Well, I want to get to here, guys. I'm sorry, I'll get to eventually. That implies that g to the j inverse is equal to the identity, which says that g to the j is equal to the identity inverse, which of course is the identity. Therefore, we have found a finite j that when g is raised to that power, it gives the identity. This contradicts the infinite order of g. No such j exists. And we find that the order of g inverse is also equal to infinity. Sorry, you do to you have to work the camera a little bit here. I've worked across worlds. Yes, it's a very long argument. Not really.
So this is a rule we have, so we're allowed to just call it this rule, correct?
Correct. Unless it's a test question, in which case you're required to replicate the arguments I just gave, yes. Like, does every question I ask have to come back to yes, and that could be a test question? Yeah, pretty much. I mean, that's the larger philosophy in here is you're, seniors in math, you want to take ownership of this course. You basically want to not just understand how to do calculations, you want to understand how to build the machinery that we're using. All right? I mean, that's what senior level math courses are about. They're about a deeper level of understanding, right? That's the goal. I do get partial credit, of course, but that's the goal. Other questions? I will tell you, part C in problem 17 is difficult. To show that something's a linear transformation in that sense, it is not at all obvious. And I've told some of you it's important. I mean, one nice way to look at, I posted a link to a video in the notes. If you actually click on that video, it says this video. It's like, depending on how you look at it, what page is it on?
58.
58. Is that right? On page 58, there's a link to a video. If you go to the 12-minute mark in there, there's a very, very significant, I'd say hint, but it's it's practically a solution to part C. But you need to understand what you're doing. It's not. I don't think it's for free or anything. It's not like that. It's not like Course Hero or something. Oh, whoa, no. Sorry, picking up the complex book. Don't want to do that.
So on number 13,
I do generally mean to be working problems from the textbook, which I recommended in here, as opposed to just fielding questions from the mission. That's not really the purpose of this session. I mean, it's fine to do that some, but we should also be doing other things, But keep doing it. I forgot to bring my book. I have no excuse, right? So, anyway, that's a thought I've forgotten to communicate to you guys, but 13? What about it? Oh.
The denominator is not.
yeah, when you try to do this subgroup, you end up with a denominator with two things in it. And it's like, how do you know the two things aren't just square?
So my advice for 13 is that problem 13, I think the only way I'm going to see through it is to take things that are from the alleged group, right? And I'm going to have to look at the prime factorization of the denominator. I'm going to have to use the fundamental theorem of arithmetic to express those denominators as products of primes, right? And since it's square free, they're not repeated, right? And then I think to make the common denominator, what we're going to do, like I gave this as a hint the other day. If you think about 1/6, like plus 1/10 or something like that, you know, if you just did the greedy thing, let's put a 7 here, and 11, whatever. If you just did the greedy thing, you'd do like 7 times 10, right? Plus 11 times 6, and you'd get what? You get, you know, over 60, whatever that is. Whatever that is, 140, 146, I don't know. Can't do math. 136? Okay. Now that would be a little bit disconcerting because that is 4 times 15, aka 2 squared, oh no, times 3 times 5. Very much not of the form we want in the group. But of course, actually, that's 2 times 68. Man, it's sad. I don't think I can do arithmetic right now. 2 squared times 3 times 5. So that's 68 over 2 times 3 times 5. So as you can see, the apparent squariness of the denominator is actually illusory. Illusory? Illusory? It's a word I can't say today. Not apparent. If we just use the greedy algorithm to add fractions, but what is a less greedy algorithm that you were forced to learn as middle school or let's say second graders? No, second graders don't learn how to add fractions? No. Aw, come on. Oh, good grief. Are you serious? 4th grade? Oh my goodness, what is this world coming to? Of course, you want 30ths, right? Learned in 5th grade. What is 30 to 6 and 10? Yeah, least common multiple. That's the way to go. So if you take the least common multiple of square free numbers, it's also a square free number. You can prove that if you don't know it already. And the way I would prove it would be, the way I would say any of these things is just look at the prime factorization of your arbitrary things you pick and then use that to go, that's what I'm going to have to do.
So we can't just pick like real examples?
No. I'm illustrating the pattern. What you want to do is something like, you got m over n, m1 over n1 plus m2 over n2, right? And you're going to need to do something like n1 is, pi1, I guess we could say p1, p2, p, pr, and n2 is q1, q2, qr. I know that these are distinct primes because these are square free, and I'd have to work with those. This is just an example to get you started. That is not the proof. No. Thank you for that question. Oh, noes.
Your definition of square free, is that just the number itself is not a square, or none of it's like it couldn't have?
It's the prime factors. It's the more complete sentence is that a number is square free if its prime factorization has no repeated prime.
Okay.
Yeah. But it is common number theory lingo. That's why I didn't. But when I wrote the question, I'm like, I can't think of how to say this. This is a well-defined term. I'll just use a word. So if I was more with it, I would have just said what I said in the problem statement. But sorry. But I personally, I'm going to have to suffer through these things. In other words, you just have to kind of explain the least common multiple way of adding fractions is what the problem actually is about. Well, it's a chance to explore that at least formally. Other questions? This is a good question, I think. Other things in there are easier, like I think once you prove closure, everything else is it's mostly just closure you have to prove there. Associativity is fairly obvious because it's still addition. I mean, the associativity is for free because it's addition of rational numbers, which is known to be associative. Negation, well, is if you have a square-free, if you have a square-free denominator, is the negative of that still a square-free denominator? Yep, so like negation is pretty easy. The only thing that's really tricky is the closure. Actually proving the sum of two square-free denominator things is actually a single fraction with a square-free denominator. Yep.
The question is to prove that it's a subgroup.
Yep.
So we can also use a test, correct?
Yeah, yeah. The supergroup, if you will, is the rational numbers under addition. If H is a subgroup of G, then G is the supergroup of H, is terminology we could use. Although supergroup has another meaning, which is divorced from that.
Right, so like we wouldn't have to test closure, invariability, identity, and associativity if we know, when
Yes.
using a subgroup.
Fair enough, yes. We could just show, it's clear it's a subset, and so,
And that's not empty.
yeah, so I guess to the one-step test, I guess you just got to put a minus here, but I don't know. I think personally I would just rather do the two-step test on this one. I don't know, just because it's confusing enough already without trying to do two things at once.
Yeah, it is
Yeah.
confusing doing one step.
Yeah. Other questions? Yeah.
It's from the notes, but in this one example, it
Uh-oh.
has phi of x. This is, wait, do I just page? So I'm just confused how we go from this step to that step.
So let's see here. I'm trying to look at isomorphisms between Z4, right, and U5, allegedly. And I'm trying to describe how we can define an isomorphism from Z4 to U5. So I say, well, I say my point is that this is generated by 1, and this is generated, additively generated by 1. This is multiplicatively generated by 2. There are other choices, but that's one of them. And so my point is, if you got a cyclic group, you can define an isomorphism if they've got the same order, just by mapping a generator to a generator. Like that's going to define an isomorphism. And basically, the idea is to force the isomorphism rule. I'm trying to think here. So, I don't know. Let's think about it this way. This is n times 1. That should be. What I'm trying to say is that defines an isomorphism. I guess I had an x. Was your question? What was your question?
Well, it goes from phi of x times 1
Yeah.
to phi of 1 all raised to the x.
Phi of x times 1 to what?
Equals phi of 1 all raised to the power of x. And I understand that you could break up phi of x times phi of 1, but I don't understand how you go from the left side of that to the right side.
Well, this is actually just a property of isomorphisms in the case that the domain has additive notation, but the range has multiplicative notation. So we proved in here that phi going from G to H, has the following rule: phi of G to the n, right, equals phi of G to the n. Like we did this in a lot of detail, right? in the case that there's a lot of different versions of this, okay, depending on our notational choices. So some notational choices, well, first of all, this is just in the case both the domain and the codomain are both multiplicative. But in the case the domain is additive, right, but the codomain is multiplicative, this is what the rule looks like. In the case that the domain is multiplicative, but the range is additive, it would look like this. In the case that what's our other case? I guess that's it. Oh, we could also just have both additive, right? That's the other. I mean, those are 4 different flavor options. Add, multiply, 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 add, multiply. Yeah.
So I have kind of 2 different questions. First of all, just on an example, example 2.4.6. You say, like in problem 37 of Gaussian, you're asked to show that a 2x2 matrix.
Yes, that problem.
All have the same elements.
Yep.
For all of them being in the reals, forms a group with respect to matrix multiplication.
Right. I'd love to talk about this problem with you guys. Let's talk about it. What is your question about it? Is it driving you?
Is it a group?
It is a group.
How?
Exactly.
That is great.
Yes, let's talk about it.
Is it invertible?
Let's talk about it. No, it's, well, that's the question, isn't it? So let's take 2 of these things. A, just that, right? I. Right, and then X, and multiply those. Your usual matrix multiplication, what's it look like? 2ax everywhere, all right. So congratulations, you just proved it's closed, right? Because the product of 2 matrices in G is again in G. Is it associative? In other words, matrix multiplication is a binary operation on G. Yeah, okay, we have that. It's also clear that, matrix multiplication is associative because it's matrix multiplication. So it's an associative operation. We got associative, we got closed. What else do we need? We need inverse, right? But before we need inverse, we need to understand what does inverse mean. In order to understand what inverse means, you must first answer the question, what's the identity? Is it? Because the identity condition would be that A times the identity matrix, whatever it is, right, is equal to A, right? So this would be E. What's E? See, we need A equals to 2ax, yeah? Which is to say that, what's that to say? I think that's say x is equal to 1/2, is it not? So E, in fact, the identity here is 1/2, 1/2, 1/2, 1/2. And so in view of that, what's the inverse? A inverse equals to what? See, because now you're asking the question, I want A times x equal to 1/2, 1/2, 1/2, 1/2. That's the condition which is needed in order to say that x is the inverse of A. What do you need for x?
The x's would be a quarter?
x's would be a quarter. Hey, was a non-zero? Okay, that's good because I need that now. See, shouldn't x be equal to 1 over 4a? Or is that, I don't know. I need that, I mean, this is, again, this is still 2ax, 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 right? I'm trying to solve for x right now. What's that give me? 1/2 equals to 2ax. Therefore, x is equal to, yeah, 1/4, 1 over 4a. So in fact, I can erase that question mark. The inverse of this is 1 over 4a, 1 over 4a, 1 over 4a, 1 over 4a. And that is an element of G because G, properly stated, is non-zero reals. So there you go. We got closed, we got associative, we got an identity, we got inverses, we got a group.
It is not a subgroup of the general linear.
That is right. It is not a sub. that is the trap.
It's not invertible.
G is not a subgroup of GL2R. No, it is not. In fact, G is not even a subset of GL2R. So you know right there. You should stop at the subset condition because these matrices have determinant what?
Undefined.
Nah, it's defined. It's 0. 0. Determinant 0. So they're not in GL2. Yeah, they're not. Yeah. So it's the tricky thing is you're tempted to think once you're thinking matrix multiplication, you're automatically in the world of GL2, like the general linear group. But that's not the case. Matrix multiplication's defined for all matrices, not just the invertible ones, so you can do other things. All right. In fact, matrices, much like permutations, are sort of a blank canvas on which you can draw all kinds of other math. Like, not just, I mean, this is, I love GL2R, but you know, there's more out there. This problem's insidious, though. I mean, this problem really messes with you, doesn't it? Yeah, yeah. It's a good problem. Was that in the homework?
No.
Okay, phew. Phew, okay, good. Because I really just solved that thing. That's here. Oops. So yeah, other questions, yeah.
Does anyone else? My other is more general.
Uh-huh.
I remember I had this problem last year as well in linear. What is your strategy when attempting to find an isomorphism or define an isomorphism for, you know that you're trying to find an isomorphism between
How to find, yeah.
vector spaces.
How to find isomorphisms? Well, there are, a lot of different answers to that depending on the context. I mean, if the group is small enough order, you make Cayley tables and make sure they've got the same pattern. And that will suggest a dictionary between the two groups, which shows that basically it's just a change of notation, right? Same pattern. If they're cyclic groups, all right, then if you can send a generator to a generator, that's going to define an isomorphism. That will become, I think, more obvious as we study cyclic groups in the next hour or two of class. But that was what Bethany was just asking about, is like, I mean, the basic idea was that the generator mapped to the generator. Then essentially I'm just assuming that the laws of exponents extend it. By so assuming, that defines an isomorphism. In the same way that I said last semester, like in linear, I say if you've got a linear transformation defined on a basis, there's a unique linear extension. Well, the same with isomorphism. If you define for a cyclic group the image of the generator to the generator, there's a unique extension which gives you the isomorphism on the whole group for a cyclic group. If the group has more than one generator, right, if it's got, like the dihedral group has two generators, the A and the B, then if you want to define an isomorphism from the dihedral group, you got to say where both of the generators go. And then I think generically speaking, I think you just have to kind of get to know your groups, right? It's not, there's no, as far as I know, general algorithm for finding an isomorphism. I just have to see it. I look for mapping things with the same order to the same order. There are some other rules, like the formula has to map the identity to the identity. So that's pretty, you know, that's a lot of, that guides a lot of it. So those are my initial thoughts. Yeah. Mm-hmm.
You said you would go over the broken corollary in class, but you didn't. Can you tell me what it's supposed to say?
Well, I'm glad you asked me about that. Well, thank you for asking me about that. That's very helpful. In order to understand the corollary, we need to understand a couple proofs. Really more. There's two ways you should read Lecture 6. All right. The one way you should read it is just to write down the results and try to like meditate upon them, because there are things you need to remember. The other way you need to look at Lecture 6 is to actually like prove the theorems in there. All right. And it's important for you to do both. I think what we're going to do today is more like just survey the results. Okay. So let's start with that. And then probably next class I will regret not having proved something here. Maybe I'll prove something here yet. Let's prove something. How about that? Here's a good one to prove. Theorem. Can you guys see that? Theorem 2.6.10, let G be a group and A, B, and G. If the order of A is infinity, then A to the I is not equal to A to the J for any distinct I and J. Right? On the other hand, if the order of A is n, then that means that the list 1A A to the n minus 1 is in fact a set of distinct elements, right? And more than that, A to the I is equal to A to the J if and only if n if n divides the difference of I and J. All right? So let's work on the proof of that. Well, actually, let me not write because I'm about to. Oh. All right. Let's just try to go through this carefully together. So if we begin with the case, did I need to zoom that out? I'll zoom it out. You didn't zoom it out, right?
No, I just kind of aimed it.
Oh, that's not bad.
Thanks.
Yeah. So I'm just going to dim the lights up here so we can see it better, if you guys don't mind. All right, so first of all, before I go through the proof, the result is like pretty unsurprising, isn't it? I don't think you're going to have to work very hard to remember this. So let's get to it. If the order of A is infinity, if it were the case that there exists distinct I and J, right? And you had I to the J equal to A to the I equal A to the J, we could suppose that I was greater than J without loss of generality. If you multiply by A to the minus J, we get A to the, A to the I, A to the minus J is that, which means that A to the I minus J is equal to E. But that contradicts that the order of it's infinite, right? So the infinite order case is really easy. Done. All right. Now the finite order case requires a little bit more work. Here we go. Suppose that the order of A is n. Then suppose we have A to the I equals A to the J for some, and I'll suppose that J is less than I, right? You can do this without loss of generality. Now, multiply by a to the minus j again, that gives us a to the I minus j. But since we have j less than I less than n, that implies that I minus j is less than n minus j. And n minus j is clearly less than n, right? Notice I and j are both positive. That's why I can say that. So we cannot have that a to the I minus j. If a to the I minus j was e, then that would contradict that the order of a is n, right? Because that would be a power less than n, which powered to the identity, which would contradict the order of a being n. Therefore, a to the I is not equal to a to the j for 1 less than or equal to j less than I less than n. All right, so that proves that that's a distinct list, right? That proves that there are n things in this list. And then it still remains to show that these are equal if and only if n divides I minus j, right? So that's what we're going on to prove. Suppose k is in the integers. Then by the division algorithm, we can pick q and r and z with k equal to qn plus r. And then if we look at a to the power k, that's a to the qn plus r, right? But then laws of exponents, a to the qn times a to the r, which is a to the n to the q. But a to the n is e, so we're just left with a to the r. So we've got a to the k equals a to the r, right? Now, let's see here. We've got 0 less than or equal to r less than n. So that means that r could either be 0, 1, all the way up to n minus 1, right? And so the cyclic subgroup generated by A is simply, oh, yeah, it's something I'm failing to, I'm an idiot. I don't know, why am I? Sorry, I'm confused all of a sudden. Shouldn't be confused. Anyway, so the cyclic subgroup generated by A is 1a squared all the way up to a minus 1. I think that's what, I'm trying to think, why didn't I know this already before this argument? Oh, I know the thing. So a to the power k, right? The Langle A wrangle, the cyclic subgroup generated by A, in principle is infinite, right? So, great. I've calculated, what I convinced myself of in this previous paragraph is that if we go from the identity all the way out to the n minus 1 power, that those are distinct. But who's to say that as you look at all possible powers of A, that there's not something more beyond those, right? That's what this division algorithm argument is showing, is that that's it. That is a complete list of the powers. Anything beyond that can be simplified to that. So there it is. Now, finally, if AI is equal to AJ for some I and j, then we can multiply by A and a to the minus j. We get a to the I minus j equal to E. And that, by the division algorithm, gives us, again, an R, which is between 0 included and n not included, with I minus j equal to qn plus r. And so when I look at it, I've got E is that, which is a to the I minus j, which is, qn plus r. But again, the n part of it powers away to the identity. And we're left with a to the r. But so we've got a to the r equals to E, where r is what? It's either 0 or between less than n, right? But since the order of A is n, we cannot have anything except for 0 in this equation, right? That forces r to be 0. But what does it mean for r to equal to 0? If r is equal to 0, that means that n times q is I minus j, which is to say that n divides I minus j. So, there you go. Now, Emily had a question about, you have a question about this?
No,
2.6. Oh, we're almost there. So if G is a group and A is in G, then the order of the element is the order of the subgroup which it generates. Well, that's nice. So we don't get confused about like having an order 3 element which generates a subgroup of order 9. That would be annoying. No, the order of the element and the order of the subgroup which it generates are the same. Yay. That's one for order. Here's the proof. If G is a group and A is in G, then if the order of A is infinity, then that we already just, by the theorem I just went through, we have that these are distinct, and so that means that this cyclic subgroup generated by A is not a finite set. So its order is infinite. On the other hand, it's also the same kind of infinity. Well, all right, I'm going to shut up about that. I don't have enough to say about that to make sense of what you said. Anyway, on the other hand, if the order of A is finite, then theorem 2.6.10 shows that that's a distinct list of elements, and then that's everything that's in the cyclic subgroup generated by A, which is to say that that has n things in it, but the order of A is n, which is to say that the order of A is equal to the order of the cyclic subgroup generated by A. Yay. All right. At this point, I share with you some really cool terminology from Rotman's abstract algebra. If you ever have a chance to read Rotman's writings, do so. He's an amazing author. He passed on a year or two ago, which is unfortunate because he's really one of the great mathematical authors of our time. Phenomenal author. And here's what he shares. This is the term theorem is from a Greek word meaning to watch or to contemplate. So a theorem is something worthy of contemplation. The term corollary is from a Latin word meaning to flower. And because flowers were a common gift in ancient Rome, I guess, I don't know, whatever. So when you think corollary, you should think, it's like giving somebody a flower, It's very romantic, really, Be like, hey, my lady, I got a corollary for you tonight, Here, a bunch of corollaries. Wow. Math game. Let's see here. Not really. Let's see here. Oh, mathematics also apparently is a classical Greek term which means to learn. It would be nice if we could get more people to learn, right? Just saying. Now finally, the offense, which is the writing of this corollary. If G be a group and A and G with order A equal to n in n, if A to the k equal to E, then n divide k. What on earth do I mean by this sentence? That's the question that we come to today. That's our final, the resting place for this help session. Let's interpret this and then we'll go home. So what do you guys think? How should I rewrite this corollary with English? Words.
Well, it makes sense because if the order of A is n, then it's only going to equal the identity for multiples of n.
Right.
So you're just saying that any number that you raise A to is equal to the identity, then it has to be multiple of n. I feel
Should you maybe say let G be?
Yeah, let's try that out. Say let G be a group and A an element of the group with the order of A equals to n for n in the natural numbers. Then if A to the k is equal to E, then n divides k. Now, to be honest, folks, the way I like to think, honestly, I don't think in divides by. If I wanted you to, to be totally honest, when I see A to the k equals to E, that to me says that k is equal to like d times n for some d, right? In other words, k, it's logically equivalent, but just for me, I think k is a multiple of n when I see that. I think in multiples. I don't think in divides by, just to be honest with you. But there are these creatures called number theorists who, like, divides by is like a native concept for them, right? They wake up in the morning and they're like, I need to divides by some coffee or something. I don't know what is it they say? I mean, we know that the love language of what is the love language of a number theorist? Primes? Prime numbers? Primes. That might make sense. They do like primes a lot. Like a little bit too much, I think. Oh, I was going AI. Okay, well, it's a good place to stop.